Okay, being recorded.
All right. It's a pleasure to finally have Wade Bloomquist from Georgia Tech at the seminar. We meant to have him last year around this time. So it's good that we finally get to hear from him. So whenever you're ready, just take it away, Wade.
Oh, okay. Well, thank you for having me. The commute is much easier these days, even though even in person, it's still pretty nearby. Um, yeah. So the first thing I want to say is, I think that in my abstract, I promised pictures. So a good place to start is a very big picture. So what we're going to be looking at, like very broadly speaking, is a type of mathematics that focuses on diagrammatic techniques. And we're going to see how this provides a place where we can look at the interplay between algebra and topology. You could call this quantum algebra and quantum topology, but really you're just looking at the same thing from two different viewpoints. So it's not a very important distinction there, but it's a picture of sorts, just kind of where we're going to be living throughout this talk. And another thing that I wanted to speak, because this was something I actually thought a good amount about, on with a seminar like this, now that we're online, kind of what's the best outcome? And I think that that means that people should ask as many questions as possible, because if you can gain some nugget of information from some piece of the talk, then that's going to be much better than if I'm able to get through absolutely everything possible to say. So stop me at any point in time. I won't ever be offended, even if I'm in the middle of a sentence or something like that. So, yeah. Just as an outline of what we're going to talk about, if we're working between algebra and topology, we should talk about where in topology we'll be working and where in algebra things will be coming from. Then we'll talk about the stated Skein module of a marked III manifold. That's kind of the very specific tool that we'll be looking at, but also object we'll be studying. So it's both a tool and an object, kind of going back and forth between those two different viewpoints. And in particular, the Chebyshev-Frobenius homomorphism, which is a fancy name for a very specific map that we'll be focusing on. And we'll want to see some kind of properties or things we can notice, both on the algebra side and on the topology side. So again, this idea that we want to emphasize and focus on going back and forth between algebra and topology, with diagrammatic techniques being that bridge. Okay. So to start off, and this is always a weird place on, if you're going to define something, how far back do you go to define it? So the approach that we're going to take is to just throw a definition up here, talk about the pieces, and then rely on kind of having these pictures in your head to guide on what this actually is. So if M is a three manifold, this can be any three manifold of your choice, then the Kaufman bracket Skein module, which is kind of a mouthful of words that just get spewed out here, is going to be, so first of all, we're working with a free module over Laurent polynomials generated by isotopy classes of framed links. So we need to break that down, right? A framed link in a three manifold is going to be embeddings of annuli, right? We're just going to have collections of annuli inside of this three manifold. And we have pictures here to kind of help us through this. They're just on the page. We don't really know what they mean at this moment, but we're looking at them. And if this is supposed to be related to embeddings of annuli, how do we read these pictures? Well, we're always going to take in our diagrams the blackboard framing convention. So you can think of just lying flat on this page, a little thickening of each of these strands. That will suddenly make it a piece of an annulus rather than just a piece of a link of something like this. Of course, you could also take a normal vector if you prefer vector fields, and then that'll just be sticking straight up from the page. Same thing, if we want a flat annulus or a link with a normal vector. So Now, what does it mean to take this free module spanned by isotopy classes of framed links? That means that our object of study are going to be linear combinations of these isotopy classes. So, okay, if we have linear combinations, we need coefficients. And in this case, I specified what R is going to be, what our coefficient ring is, and they're going to be Laurent polynomials in Q. So that's a perfectly fine thing. We just have linear combinations with our scalar multiples being Laurent polynomials. Now that's a pretty big space, and we are going to take a quotient by these two relations. So you look at all of these linear combinations of all these isotopy classes of framed links, and we impose two additional conditions. This first one is we can resolve a crossing. So inside of a ball, that's how we want to view this first condition here, is this is happening inside of a ball. So everything is happening inside of that ball. So we have some ball inside of our three manifold. There's two, there's kind of locally, we have this crossing occurring, and we can resolve it in two different ways. So everything outside of the ball is staying exactly the same. And then inside of the ball, now we have a linear combination of two different framed links that have been changed in these two ways. And notice that Q and plus Q inverse there, those constants for our linear combination are very simple Laurent polynomials, right? And then the second condition is going to be, we can pop a bubble, I guess we'll say, if you just have this, you just have a unlink, kind of an unknot component there, bounds a disk in our three manifold inside of this ball, we can pop that for a factor of negative q squared minus q to the negative 2. That's not particularly important, but we note that that is indeed a Laurent polynomial in Q. So yeah.
So wait, it looks to me like using these relations, everything could be boiled down just to a polynomial times the empty diagram. Is that true?
So I am glad you asked this question, and I want to use it to have some thunder stolen and jump to the next slide.
I'm sorry. I
No,
apologize.
that's wonderful. That's fantastic. That means you're engaged and you're paying attention. And
Oh, but that's because that's in S3. I see. I see. I was so in general manifolds is more interesting, right? But again, the diagrams are in balls projected onto disks.
yes, fantastic. Just that local relation is being determined by everything outside of that's happening the same, but we're paying attention to a local ball projecting onto a disk to make our lives easier. But so inside of S3, as was noted right here, an excellent observation, we can take any link, it's living inside of a ball, we can apply our local relations one at a time, resolving crossings until we get a sum of just closed loops. And then, well, I guess everything's a closed loop depending on your perspective. Just a sum of these unknots, and then we can pop each of those bubbles to give some, I mean, there's simplification that could happen, obviously, but it's not really relevant for our conversation. It's a Laurent polynomial in Q times the empty diagram. So for S3, what we just described exactly was the Kaufman bracket polynomial. You have a framed link inside of S3, and using these relations, we can resolve down to a Laurent polynomial. It's called the Kaufman bracket polynomial, but maybe it should be called the Kaufman bracket Laurent polynomial. But that's not an important distinction. But yeah, excellent observation. And this is kind of our starting point for three manifolds. If you don't understand it for S3, probably difficult to understand it for other three manifolds. Yeah. Are there any questions about this? We're good here? Okay. So then, well, what about something that isn't S3? We just go to a genus 1 handle body. This is a perfectly fine framed link inside of there where I'm being a little, I mean, I should have done something to indicate that this is, you know, a solid torus that's living inside of there. Really, the same example is going to work if this is a torus cross an interval. So I didn't want to really make too much of a fuss about it. But the idea is, this is just equal to itself, right? There's no further resolution, no further simplification that can be made here. There's no crossings to resolve, and well, none of our, nothing bounds a disk to be resolved by our popping a bubble condition like that. So we're left with something that generalizes the Kaufman bracket polynomial in a way, but you're not just going to get down to a single Laurent polynomial times the empty diagram. You're going to get to eventually, right, Laurent polynomial coefficients on certain basis type diagrams. Not quite a basis, but we'll talk about situations where we can talk about that more. But this is just to show that this is specifically an example to emphasize you're not always going to resolve down to the empty diagram. And that's kind of important. So, yeah. Okay. Not a very exciting example, right? This is something where it's just equal to itself. But it emphasizes the difference between different three manifolds. It's not S3, something a little more interesting. Okay. So now we're talking about three manifolds. So how do I talk about the Skein algebra of a surface if our world right now is three manifolds? Well, you do the same thing for the surface cross an interval. That's a wonderful module where we just construct all of the framed links inside of the surface cross an interval, but there's additional structure. And that additional structure is given by vertical stacking, because as soon as we have surface cross an interval, we have a notion of above and below, and multiplying two curves, well, we can put one on top of the other. There's a slight ambiguity in the moment on if multiplying stacks the left on top of the right or the right on top of the left, but we don't need to worry about it. So here we see a nice picture where on the left we have just the meridian times the longitude of the torus here, where this is happening inside of the torus cross an interval now, where on the previous slide, this same kind of picture looked like a genus one handle body. Now we really do want this to be a torus cross an interval where we're projecting onto one of the pieces. But so when we take this multiplication, suddenly we have a crossing that we can resolve. So now this multiplication of two framed links becomes a linear combination of framed links. And we can note this theorem right here, which primarily is included, well, first of all, because it's a nice thing, but it also gives a nice sense of the time frame about when these kinds of objects were first introduced and when these kinds of fundamental theorems about them were proven. So originally, Shatitsky in 1999 proved that we can give a basis for the Skein algebra, meaning there's no torsion, so it's actually a free module. And we can understand this entirely by looking at simple diagrams, meaning diagrams without crossings on the surface. And we have the diagrams of multi-curves on the surface itself. So for example, up above, you see that multiplying the meridian and the longitude is giving us this linear combination of like the 1, 1 and the 1, -1 curve on the torus.
So it's important here that the meridian is below or inside of the longitude.
Oh, so if it was the other way, right, then these powers would just be
Would switch, right?
So it's not particularly important. Like if we think about it, there's this defining variable q. We're working over Laurent polynomials in q. Is that any different than working over Laurent polynomials in q inverse?
No, but you have chosen it to
Yes.
mean this way. Yeah. Okay.
It's almost like do you multiply braids from the top down or from the bottom up? So it's not a particularly important convention, but you do have to choose one of them. And yeah. And this yeah. Okay. So this gave us kind of a nice background in the type of topology that we'll be thinking about. And as I mentioned, we do need a little bit of background algebra as well. So if we have players in the game who are topology, we have their opponents, if you want to think about it like that, as things in algebra we need to think about. This is almost like if you're not familiar with the language, a very complicated way of describing a very simple object. So I call it our favorite coordinate algebra, but in this context, maybe our actually just means my, and you're along for the ride. So you have to adopt it as your favorite coordinate algebra as well. But we like 2x2 matrices with determinant 1. Like that's a nice object to study. Right, this is just SL2. An algebraic group is not important. You can think Lie group, but really it's a group that's also an algebraic variety. Not super important. If you like manifolds, that's fine to think Lie group instead. Now, the coordinate ring, or coordinate algebra if you prefer, of this algebraic group is really easy to describe. Right here, well, when we write this piece right there, we just have polynomials in 4 variables that commute. So that's a really simple thing to talk about. And we have one additional constraint, and that's that AD minus BC is equal to 1. This is, of course, just the determinant constraint. And this might sound like okay, that's a really weird way to describe something pretty simple. And it is, right? Because these coordinate functions on this algebraic group are just picking out the entries of a matrix. So A, this first variable there, is just picking out the 1/1 entry of a matrix. B picks out the 1/2 entry, C picks out the 2/1, D picks out the 2/2 entry. And then this relation between these coordinate functions is exactly just saying, oh yeah, we have that this is a matrix. The entries commute because they're just over some ring, some commutative ring. And we have one additional condition on our entries, and that's that the determinant is 1. So this is a very simple algebraic object. But I do want to stop just to check if there are any questions about this way of describing this.
So, sorry, O of SL2 is not SL2.
O of SL2 is not SL2.
Okay.
It's not the 2x2 matrices themselves. It is the coordinates, it is the entries of the 2x2 matrix. Yeah. Slight difference, but kind of an important one. Yeah. Okay. So if we have a favorite coordinate algebra or coordinate ring, if you prefer, then I have to do it. Our favorite quantum coordinate algebra. This word right here in this context will almost always mean taking something that we know and was our favorite, that was commutative, and breaking that commutivity to Q commutivity. So right now, we still have this algebra is generated by 4 things, A, B, C, and D. But this isn't just polynomials and commuting variables anymore. Now we have to pay attention. A and C no longer commute, they Q commute. Similarly, A and B, similarly, B and D, similarly, D and C. So these are our Q commuting variables now. And we also don't quite have the determinant relation anymore. We have what you might call the Q determinant relation. So something to point out, if Q is equal to 1, well, we just get right back to our previous example of our favorite coordinate algebra. And that's kind of an important property that we want to keep in mind, is that this is creating a one variable family of algebras that deform, whatever that means in this context, away from, well, something that was kind of classical, like we understood well, we liked, we want to work with that, and we want to extend it forward. There's not much information here, right? I just defined an algebra. So there's not really too much to say because it's just generated by some 4 things subject to these relations. So I guess the question would be asked, are there any questions about these relations?
Is Q a generator too? So now we really have 5 generators?
Q is not a generator, right? So Q is a distinguished element in R, right? So Q is actually in R, right? Q is just you want to think about that as
But
a.
if I want to define it, then I have to have A, B, C, D polynomials in them, and I have to have this Q.
So, yeah,
And then I have also AQ and BQ and CQ. And do I have Q squared?
yes, right, because Q squared is just an element of R. So that's a great coefficient to put in front of whatever.
But so I could think of it that it isn't generate. Couldn't I? I mean, isn't it really generated by A, B, C, D, and Q with these relations?
Not exactly right.
A, B, C, D are not elements of the ring.
Mhm. A, B, C, D are just generic.
It's the difference between vector and scalar.
Oh, okay.
Is there an underlying set of objects like the matrices that this thing is acting on?
Okay, I'm being stupid. Okay.
No. It's in particular, if you haven't thought about this even recently.
Yeah. Okay. Yeah.
I have a question. So normally you would expect when you set Q equal to 1 that you would get back the original coordinate algebra, but you don't have that A and D commute or B and C commute when I do that with these relations.
Don't we get that when Q is equal to 1, then AD is equal to BC plus 1, and DA is equal to BC, or CB plus 1 as well?
Yeah, I think you need one more relation, don't you?
Oh, we do need one more relation. Thank you. We have that BC equals CB. They just honest commute here as well. Sorry, yeah.
So is there like a canonical procedure that like takes you from an algebraic group to OQ of that group? Or one can imagine somebody else saying that they want to impose different commutation relations than this. Like, is there something that would make these manifestly better?
That's an interesting question because there are different deformations you can make, right? In particular, this is a one family deformation, and different choices, which I think is kind of what you're hinting at, is there's a lot of different ways you could do this. There are other families that are studied often, including 2-parameter deformations, where you're able to Q commute and then I guess Q prime commute some other things, and it can be a little bit more. So this is maybe the simplest way of doing it, and this is a way that generalizes very nicely to, very nicely to at least OQSLN, because we can do basically this exact same thing just for matrices, SLN matrices, and then it's the same process of just picking up the entries of that matrix, and then we just work with minors, like 2x2 minors. We want to have the same picture and then extend all n by n matrices there. But there are different ways you can do this. That's true. Yeah.
So the last 2 equations could be written as AD minus DA is QQ inverse. So is 0. What am I seeing there? No, busy.
D minus DA. There is a relation there, but it's a little bit more complicated, right? You get that like AD minus DA.
Is CB times Q plus Q inverse or something.
There we go. Yeah, yeah.
Mhm.
Just taking the two relations and kind of like.
Yeah, okay. I didn't see the plus. It looked like a minus, so it said 0. So sorry.
Yeah, yeah. So now I promised a lot of pictures in this talk. There does not seem to be a picture here. And in particular, I don't even have an underlying topological structure where this is at least the coordinate ring of, right? We kind of just deformed away and we were like, well, it worked for the classical case. So for like my own personal interests, that's an issue. It might not be an issue, especially to maybe anyone here or to algebraists, but I would like a better way to understand this kind of algebra. And fortunately there is, and we'll kind of get there. And it's one of what I think is the best motivations for studying stated Skein algebras. But that's almost like that's almost revealing the punchline before we get there. But yeah, okay. So now non-commutative algebras can be tricky. I'm sure that this is something you believe without much motivation. Commutative is obviously easier, so non-commutative can be a little bit unpleasant. It's just harder to work with. So two techniques that I think are worth just mentioning are you want to look at the commutative part, the center of that non-commutative algebra, and then try to understand the structure over the center of that algebra. It's kind of a natural thing to do. We like commutative. This was non-commutative. Can we carry over some of the things that we know? And then a different approach is to embed this into something that we do understand a little bit better. But of course, how do we embed something non-commutative into something commutative? That doesn't make sense. So what do we mean by nicer? And we can answer that question pretty quickly, but these are just kind of two general techniques. Non-commutative is a little bit unpleasant. So we like the center of non-commutative things, and we like to look to embed non-commutative things into highly structured objects. Okay. Yeah. And what we mean usually by highly structured objects, and this is unfortunate. It's kind of unfortunate notation for a very easy thing. So when we say a quantum torus, what we mean is Q commuting variables, just Laurent polynomials and Q commuting variables. So before we had commuting variables, that was a particularly nice thing where we originally started with the coordinate algebra of SL2. And then we moved to things that Q commuted and this determinant relation, which as we noted, gave some messy kind of commutation relation between A and D, and it was a little bit unpleasant. But quantum tori are the situation where you just have Laurent polynomials in some variables, and all of those variables Q commute up to some power of Q. That's determined by some kind of skew symmetric integral matrix. We don't need to worry about that right now necessarily. The idea is when we say quantum tori, we mean Laurent polynomials in Q commuting variables. It's not necessarily believable that that's particularly a lot more structure, but it's not less, right? It's something that we could hope to gain information from, but I'm not really telling you what that additional information is. So it's just something to keep in mind on studying non-commutative algebras. We like to embed them into nicer, highly structured things. Now, I mentioned Chebyshev-Frobenius homomorphism at some point, maybe in the outline. Well, here's something in the study of quantum tori that kind of comes up as a Frobenius homomorphism. That's almost foreshadowing in some sense. But this is a relatively simple map. This is just saying that we have this map that sends one of these Q commuting variables to its nth power. But now the nth powers of two different variables no longer Q commute. In the image, each one Q commutes, and that's n squared because you have to pass n things over n things. So they Q to the n squared commute, which is why the domain of this, you're not Q commuting, you're Q to the n squared commuting. And then in the image, you also Q to the n squared commute just by raising that to the nth power. So you have the same commutation relations with Q commuting. You can do this kind of procedure. But the key takeaway from this is, here's a very strong kind of algebraic map that appears in a highly structured algebraic setup. That's kind of the key takeaway from that slide. Are there questions on quantum tori? Okay. So now a different Frobenius morphism is working with coordinate algebras, as we have for SL2. We can, and this is a condition on the order of Q being odd, but you can just think about it as a root of unity, and some subset of roots of unity make this map work out particularly nice. But doing almost the same thing, we can put the classical coordinate algebra inside of the quantum coordinate algebra, doing this same technique of, okay, send the generators to their nth power. And an important thing to notice is that the image of this map is in the center of OQSL2. And that's a pretty easy thing to observe, because you have a to the n needs to commute with b, say, but every time you move one copy across, you pick up a factor of q. You're doing that n times. You pick up a factor of q to the n. We said n was the order of q. So it's 1. It's a little bit harder to convince yourself about a and d, because we saw that, okay, wait, there was some messy commutation relations, but I do promise with a quick induction, you can work that kind of thing out. So this is a very classical kind of construction. This on just coordinate algebras. You're embedding the classical coordinate algebra into the center of the quantum coordinate algebra.
Why do you need n to be odd?
If it's not, you can run into some issues where actually things are just skew commuting, but it's not particularly important.
It's the determinant relation.
Is it the determinant relation? I think the answer is to yes, but I'm not entirely sure. I see the full question there. Is it the determinant relation? Yes, yeah. So we should be good there. But that's just kind of the idea. It's a small thing. You can fix it. And in particular, in our formulation of results later, we'll tweak the condition that we put on the order to make things work out for all possible orders. But this is just the simplest thing. If you wanted to, you could put, we could phrase this as a result on O embedding into the center, and also a separate result about O subscript -1. So Q being -1 being, but it's not particularly important. There's just a little bit of a subtlety for other roots of unity, but we can address that subtlety. Okay. So now this is a generic thing about algebra that I just want to mention very briefly. We're comfortable with multiplication. That's an algebra, tensor and algebra to itself. You just take two things in the algebra, you piece them together, and you get out a new element of that algebra. And we like actions. So you have the algebra and something in a set, and that's just going to give you back a new thing in that set. These are great maps. And it's often useful to reverse the arrow. In particular, co-multiplication is a map from, you take a single element of your co-algebra, and it spits out a pair of elements. And a co-action is taking a single set and then spitting out an element of the algebra and an element of the set. I'm not sure just how familiar people are with working with co-multiplication and co-actions and things like this, but this is important structure that is around. And in particular, you could extend it even further, and you could say that these OQSL2, that algebra that we're working with, is not just an algebra, it's also a co-algebra, and is not just a bialgebra, it's also a Hopf algebra. And you can put more structure on there that we don't necessarily need, but it is there, so it's nice to at least briefly mention. Okay. So now we can head towards actually defining the stated Skein module of a marked 3 manifold. So a marked 3 manifold is just going to be a 3 manifold along as with a collection of markings on the boundary. So we're taking some collection of these arcs on the boundary. We can call them closed arcs, or they can be open arcs that are, it's not an important distinction there. The idea is that they're just markings on the boundary. And then we can call a kind of this, we can call a tangle in here as a framed 1 manifold. So this includes components that might just look like framed links. So the kind of original idea of a Skein module is still very present, but we're also including these arcs. And these arcs in this 3 manifold are just going to connect between the markings on the boundary. These could come back to the same marking. They could go off to a new marking. It's just a framed 1 manifold. And we're additionally going to add the information of a state for every tangle. So a tangle is stated with, there's an assignment of plus or minus to each endpoint on a marking. And we can see from this picture right here that this is a thing we can do, right? Here's an excellent stated entangle inside of our marked 3 manifold M. So yeah. Are there questions about this definition or these definitions?
Is it sort of assumed that the tangle, each strand of the tangle is like a little annulus? So like the annulus is lining up with the little arc on the boundary?
Yes, yes. So there is a condition with the compatibility of the framing with the tangent vector of the marking on the boundary. And it was swept under the rug a little bit, but yes, yeah, absolutely. And if you prefer if you prefer to think about framings as a normal vector matching with a tangent vector, that works. Or you can think about it as the small annular thickening, and then that matches into the marking itself. Yeah, equivalent ways to think about it, but an important compatibility condition.
And the plus or minus is independent of orientation choices.
Yeah, oh, that's an excellent point. Yeah, this is not orientation. This is not saying that we're going from minus to plus or vice versa. And in particular, like this example drawn here, they're both plus. It's just additional data. It's an assignment of a plus or a minus to those boundaries. You can go from plus to plus, you can go from plus to minus. You can, yeah. Okay. So now we have our analog of framed links inside of a marked 3 manifold. So we need to introduce relations if we're going to define the stated Skein module, right? And the same relations that we had before, resolving a crossing and popping a bubble, still hold. The only thing we need to do are adding these new relations on how to deal with these arcs meeting the boundary markings. So the same setup of Laurent polynomial linear combinations of these tangles is still in play. There's not a big jump there, so you can have the same kind of idea in your head. But now we have these 2 additional relations, or these 2 additional, it's 3 relations on how to deal with arcs coming back and arcs coming to boundary markings. So this is just two different ways that you can look at the picture. The one is a top view where you're kind of, you've projected down and you're looking at your marking kind of coming out of the page on the left. And the same picture is given on the right as, okay, you're actually just looking at this as a side view now. So you can see this is a, on the left top here, we have a tangle that meets a boundary marking and then comes back with a plus above a minus on that boundary marking. And this evaluates to a constant times the empty tangle. This is like popping a half bubble, so to speak. And that same picture in the side view, we have a plus above a minus, a plus above a minus. Okay, we can just pop that bubble. And if in one of these returning, these trivial returning arcs, you have the same states, that's 0. That's not the empty diagram or anything like that. It's just flat out 0 in this module. So it's the 0 linear combination. And then this last relation that we want is like a height exchange relation. You're able to, it's maybe easier to see in the side view picture, where you're able to take a minus that is above a plus and just slide it down at the cost of a q. And these are just relations as before. We had, you could actually use the resolving of crossings relation to give a little bit more information here, but we don't necessarily need to. So now this was the stated Skein module. Now, this is an important property that I want to mention, and this is we're always going to have a well-defined map given by embedding. This is an important technique, and I wanted to specifically mention it because it's how a lot of these things are proven, that a lot of these like well-definedness properties about homomorphisms, the Chebyshev-Frobenius homomorphism, that's kind of like the punchline of today. If we're going to prove well-definedness, this is what lets us look at easier pieces. There's always a well-defined module map given by embeddings of marked 3 manifolds. So you can work in a simpler case and then put that into a more complicated 3 manifold. Okay.
Excuse me.
Yeah, absolutely.
This embedding is so it's embedding the boundary. I see. So M, you're just taking pieces of the boundary of M and embedding them into M prime.
Yes. So the markings.
Not all of the components. The boundary, you don't have to match boundary components somehow. You just.
That's true. Yes. Yeah. You only need that the boundary components actually embed into the boundary components of the other one. So hypothetically, you could send the pieces to the same boundary component in N prime as long as you're embedding each slice into them.
But could you embed a ball into a closed 3 manifold?
Could you embed
like this thing on the left, right? You have the vertical bit of the boundary. Where does that vertical bit of the boundary go? Of the ball.
Vertical bit of the boundary. This thing. Oh, you're talking about like this piece right here.
Yes. Mm-hmm.
So that's not included, right? This isn't closed. This is open.
I see. So your M can be open.
Yeah. Or yeah. So this right here, the boundary itself is actually just.
But M doesn't have to be a compact manifold with boundary. It can be non-compact, and the boundary can be non-compact. Okay.
But a closed, a compact ball with boundary, you could not embed that into, say, a closed 3 manifold without boundary.
Yeah.
Yeah, markings got to get sent to markings, otherwise you're not going to have a well-defined map.
But the whole boundary has to get sent to boundary, right?
Yeah.
So like,
In order for it to, yeah. You'd say a proper embedding. In order for everything to be well defined, yeah, the boundary is going to be sent into the boundary. So this piece right here, right, is sent to say this piece of the boundary over there. And then this like non-existent gray line could
okay,
be.
but so somehow if M was compact, I mean closed and not open, then you couldn't really send it to anything. It has to be open, right?
And you want nice conditions about taking the closure, behaving well with taking the closure.
Yes.
Okay. Well, okay. So now marked surfaces are a great case. Just like when we had a 3-manifold, we were able to go to an algebra by looking at a surface cross an interval. Similarly here, we have the stated Skein algebra of surfaces is just a marked surface cross an interval to give a marked 3-manifold. And this was originally studied by Tang in 2018. Much of this work is joint with Tang, and the extension to 3-manifolds is kind of like something that this project was really focused on. But it was originally introduced in the case of surfaces in 2018, and it's just now kind of being extended to these marked 3-manifolds. But we have an analog of that multi-curve basis theorem for just original surfaces here, where we have diagrams with nice conditions on how the states behave on the boundary. But it's not particularly important. The idea is this is just a theorem that gives a basis for stated Skein algebras. Now, skipping forward a little bit, this is an isomorphism not due to myself that I think really motivates the study of stated Skein algebras incredibly well. Because the stated Skein algebra of the bigone, meaning just the disk with 2 boundary points, like there are 2 markings on the boundary, is OQ squared SL2. So now we have an algebraic description and this topological interpretation. But I'm running short on time, so I'm kind of speeding up quite a bit just to get to some things, but that's okay. It's okay if I don't quite get to much, but I really do want to emphasize that I think that this is an incredibly important result, right? This is really the motivation behind a lot of this. We took this OQSL2, and then here is a fantastic topological description. Okay, so now splitting along an ideal arc, this was a result of Tang's, and this was his motivation for originally defining the stated Skein algebra of a surface, is that when you introduce states onto the boundary like this, you can cut along ideal arcs. So suddenly now you're sending just diagrams on the surface to a sum of these over all of the possible lifts, meaning the potential states that you can get when you cut across that diagram. Okay, not particularly enough time to go into a lot of details on that, but just one of the first things that we did, so this allows you to describe a coaction for stated Skein algebras by OQSL2. Just remember that an action gave us the algebra, and a set maps to the set. Here we have the set, in this case in algebra, maps to the algebra itself, nothing has changed, and the bigone, which was OQSL2. So you can just cut off a bigone along any marked point. Now, something that we did, this is finally to kind of get to just a couple of results here, is you can do this for marked 3-manifolds by cutting along a properly embedded disk. So if you take a choice of one of these kind of a properly embedded disk, in the same way, you're going to split the tangle that gives a sum over the lifts. So this is kind of a way to try to decompose this complicated algebraic structure into smaller pieces by cutting them up along disks. It's a very intuitive kind of algebraic or kind of topological construction. We want to cut along disks to simplify things. And here we give an algebraic way of understanding this module by cutting along disks.
And it's independent on how you decide to make the arcs line up with the marked line?
Yes, yeah, right. So,
Okay.
yeah, it's independent. You do have to choose a marking in that disk for things to pass through, just to make life easy, but it doesn't depend on that choice. And so just a quick kind of, the idea of kind of how you do this, very roughly speaking, is you're going to want to look in a neighborhood of that disk and then try to reduce down to the case of surfaces by looking at a collared neighborhood of that disk. And this doesn't give much information, but it's kind of at least very vaguely the idea of the proof. Yeah, but I do want to skip forward just a second here. Similarly, then, this gives you that all stated Skein modules are co-modules of OQSL2. In the same way, you just look at one of your markings, blister inwards a little bit, and cut along that disk. You get a ball with two markings. That's a bygone. That's OQSL2. So you have a nice co-module structure on the stated Skein modules. Okay. But, okay, so now threading, this is just a way of defining the Chebyshev Frobenius map, so it's something that we're going to need. This is saying you want to take powers with respect to your framing. Inside of that annulus that this is the thickening of, you want to take powers in there and not with the algebra structure. Notice that this right here is not alpha 2, but not particularly important. The Chebyshev homomorphism, this is taking a framed link and replacing it with powers in that annulus by just the, by Chebyshev polynomials. So that's great. This is a classical thing that was studied for unmarked, just original Skein modules and Skein algebras by Bonahan and Wang. And this is super important in particular because it helps you understand the structure and representation theory of Skein algebras and Skein modules originally by relating it to the classical case. This is the same kind of picture that we saw with OSL2 mapping into OQSL2. This is mapping the stated Skein algebra at quasi-classical roots of unity into the general Skein module. And in the quasi-classical case, you can think of stated Skein algebras, say, as the algebras of regular functions on the SL2 character variety of a surface. So you're now trying to build the representation theory and understand the structure by understanding that embedding. So now this is where I'm going to end because we're short on time, but we were able to extend this to these marked 3 manifolds. And it's really almost by looking at using that functoriality to understand the crossings in small cases, understand how we can then embed that into the marked 3 manifold and work things out there. So you do the same thing where links are sent to Chebyshev polynomial threadings of framed links. So that's the same classical Chebyshev homomorphism that Bonahan and Wang worked with. But now arcs are sent to this copy of the framed power of A. So A as just an arc gets into A to the N. And in your head, you want to be thinking about, oh wait, that Frobenius homomorphism for OSL2 was very similar to this. And something worth noting is that this commutes with the splitting homomorphism along a properly embedded disk. So that's also kind of a nice property with this structure. But I think this at least gives the results to end. Hopefully things made sense in the beginning, at least before we had to zoom through some stuff at the end. But I'll open things up to questions here.
Let's first all thank Wade for a great talk. All right, any questions?
So do you get like marked 3 manifold invariance or something from this?
Yeah, right.
So
So that's something, yeah, the stated Skein module itself is a marked 3 manifold invariant. And that's kind of a property of the functoriality that we talked about. Because if you have a homeomorphism, like an embedding into each other, well, then you'll get an isomorphism of modules.
Yeah, so like, do you plug in like the value for the variable in a given, like I remember that, didn't Licorice do something like this when he did the three manifold invariance from the
So you're asking about looking at like the evaluations of, say, Jones polynomials at roots of unity, and then
Yeah.
getting surgery invariant for three manifolds in this one?
yeah. So like, yeah.
So this doesn't quite give you that, right? Because this is almost not quite going the full, like we don't have a link invariant that is invariant under Kirby moves or something like that. You're not really getting a surgery invariant to give a like numerical constant. You're associating the whole module to this three manifold. So it's kind of like going all the way back to, we said, oh, the Kaufman bracket gave a polynomial in S3, but then as soon as we went to other three manifolds, we were getting linear combinations of these kind of essential loops, and you weren't boiling all the way down to a single polynomial. So yeah, the whole module is the invariant.
Are there any good ways to compare the modules you get? Like, are they explicitly computable in any way, or?
Yes, yes, and in particular, it's because of that coaction, and this is like almost hidden in the background on everything. A coaction of OQSL2 secretly gives an action of UQSL2. So if you have ever heard talks about quantum groups and you like the quantum group UQSL2, then this is actually just a representation of UQSL2. And you can decompose that into the well-studied representation theory of UQSL2. If that answers your question.
I think so. Yep. Thank you.
I think this is a good place to pause the recording. So let's thank Wade again. And I guess if you
Hold
could
on. Pause recording.